Imagine standing completely still, no car moving beneath you, no aeroplane crossing the sky, no rocket carrying you into space, just you, standing quietly on the surface of Earth. It feels as though nothing is moving. But that feeling is one of the greatest illusions in the universe. Right now, Earth is spinning beneath your feet at incredible speed. At the same time, our planet is racing around the Sun. The Sun is orbiting the center of the Milky Way, and our entire galaxy is being pulled through the universe by forces acting across hundreds of millions of light years. Every second of your life is spent aboard a planet moving through space at speeds almost impossible to imagine. Yet we never feel it, we never hear it, and we never see the enormous path we are following. Tonight, on What If Beyond, we will uncover how fast we are really moving through space. We will explore the rotation of Earth, our journey around the Sun, the motion of the solar system through the Milky Way, and the mysterious direction in which our galaxy is traveling. But where are we actually going? Is there a fixed destination ahead? And could anything in the universe ever be truly motionless? Before we continue, tell me in the comments, what time is it where you are right now? And from which city are you listening? And if you enjoy calm documentaries about space, time, and the mysteries of the universe, consider subscribing to What If Beyond. Now, dim the lights, get comfortable, and let us discover how fast we are really moving through space. For most of human history, people believed they were standing on a motionless world. The sun appeared to rise in the east. It crossed the sky. It disappeared in the west. The stars returned every night, following the same familiar patterns. Everything seemed to revolve around Earth. It was a reasonable conclusion. After all, when you stand on the ground, nothing feels like it is moving. The trees remain still. Buildings do not shake. The oceans do not spill into space. Even now, despite centuries of scientific discovery, our senses continue telling us the same story. They tell us we are stationary. But the universe tells a very different story. The moment you opened your eyes this morning, you were already moving. Not walking, not driving, not flying. Moving, because the planet beneath your feet never stops. Earth is constantly rotating. Every 24 hours, our world completes one full turn. That rotation creates day and night. It creates sunrise and sunset. It determines the rhythm of life for nearly every living thing on the planet. Yet because everything around us rotates at the same speed, we do not notice it. Imagine sitting inside a perfectly smooth airplane, flying hundreds of kilometers per hour. If there is no turbulence and no window, you might feel completely still. Only when you look outside do you realize how quickly you are moving. Earth works in a similar way. We are passengers inside an enormous vehicle. The difference is that this vehicle is more than 12,000 kilometers wide and carries billions of people at once. At the equator, the surface of Earth moves at approximately 1,670 kilometers per hour. That is faster than the speed of sound, faster than many military aircraft. Someone standing on the equator is traveling faster than a bullet fired from some firearms. Yet they feel absolutely nothing. A person in Ecuador, Kenya, Indonesia, or Brazil is constantly moving at this tremendous speed simply because Earth is spinning beneath them. The farther you move from the equator, the slower that rotational speed becomes. Near the poles, the motion is much smaller. Imagine a spinning record. A point near the edge travels farther during each rotation than a point near the center. Earth behaves the same way. Every location completes one rotation in 24 hours, but different locations travel different distances. This means not everyone is moving through space at exactly the same speed. Your location on Earth changes your motion. Even while you sleep, your speed depends partly on where you live. If an astronaut could somehow stop Earth from rotating instantly, the consequences would be catastrophic. The atmosphere would continue moving. Oceans would surge across continents. Winds would become unimaginably powerful. The planet's familiar environment would be transformed. Earth's rotation is not merely a detail. It is part of the foundation of our world. The weather patterns we experience, the shape of ocean currents, even the slight bulging of Earth around the equator, all result from this constant spin. But Earth's rotation is only the first layer of motion. Once we recognize that our planet spins, a larger question appears. What is Earth itself moving around? The answer is the Sun. Our planet follows an orbit around its star, completing one revolution approximately every 365 days. That motion creates the year. It determines the changing positions of the seasons. It influences temperatures, climate cycles, and biological rhythms. Yet the speed involved is far greater than most people imagine. Earth travels around the Sun at roughly 107,000 kilometers per hour. Every second, our planet moves nearly 30 kilometers through space. By the time you finish reading a single sentence, Earth has already traveled farther than many cities are apart. In 1 minute, it has crossed thousands of kilometers. In 1 hour, more than 100,000 kilometers. And still, we feel nothing. Again, the reason is simple. Everything near us shares the motion. The atmosphere, the oceans, the mountains, the buildings, our bodies, everything travels together. There is no sensation of speed when all nearby objects move in unison. This orbital motion creates a fascinating reality. Earth never returns to the exact same location in space. 1 year from now, our planet will return to roughly the same position relative to the Sun. But the Sun itself will have moved. The galaxy will have moved. The universe will have changed. Every birthday marks not a return to a place, but a return to a similar stage in an enormous cosmic journey. Many illustrations show Earth's orbit as a neat circle around a stationary sun. While useful for teaching, these images hide a deeper truth. The Sun is not standing still, neither is anything else. Imagine throwing a ball to someone sitting on a moving train. The ball follows one path relative to the train and a completely different path relative to the ground. Earth's orbit works the same way. Viewed from one perspective, it circles the Sun. Viewed from another perspective, it traces a spiraling path through the galaxy. Every planet follows the Sun as it travels. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. All of them are moving together through space. The solar system is not parked somewhere in the universe. It is traveling. And the speed of that journey is astonishing. To understand it, we must leave the scale of planets behind and begin looking at the larger structure surrounding us, the Milky Way. When people imagine the galaxy, they often picture a beautiful spiral seen from above, a glowing island of stars floating in darkness. That image is correct, but it is difficult to appreciate its scale. The Milky Way contains hundreds of billions of stars, perhaps even more. Its diameter stretches across roughly 100,000 light-years. Light itself requires 100,000 years to cross from one side to the other. Human civilization has existed for only a tiny fraction of that time. Our Sun occupies a position far from the galactic center. It resides within one of the spiral structures, orbiting the core of the galaxy, just as Earth orbits the Sun. But the scale is incomparably larger. The Sun takes roughly 225 million years to complete a single orbit around the Milky Way. Think about that. When dinosaurs walked across Earth, the Sun occupied a different region of the galaxy. Entire species have appeared and vanished during only a small fraction of one galactic orbit. Human beings have existed for less than 1,000th of the time required for the Sun to circle the Milky Way once. And yet, despite this enormous orbit, the speed is incredible. The Sun moves around the galaxy at approximately 828,000 kilometers per hour, more than 800,000 kilometers every hour. At this speed, the Sun could travel from Earth to the Moon in less than half an hour. Every planet follows this motion. Earth follows it. You follow it. At this very moment, you are moving around the center of the Milky Way at a speed difficult for the human mind to visualize. But the galaxy introduces another important idea. Speed is always relative. If you sit beside another passenger inside a train, both of you appear motionless relative to each other. Yet someone outside sees both passengers racing across the landscape. Similarly, Earth appears almost stationary relative to nearby objects. The solar system appears organized and stable. But viewed from another galaxy, everything inside the Milky Way is moving rapidly around its center. Motion depends partly on perspective. This realization confused scientists for centuries. People naturally wanted to know what was truly stationary. What object served as the fixed reference point for the universe? Earth? The Sun? The center of the galaxy? Eventually, science revealed something surprising. There may be no universal stationary position. Motion only has meaning relative to something else. Earth moves relative to the Sun. The Sun moves relative to nearby stars. The Milky Way moves relative to neighboring galaxies. Every frame of reference reveals a different motion. There is no giant cosmic platform sitting underneath the universe. No invisible floor marking absolute rest. The universe is dynamic everywhere. Everything moves relative to something else. This concept becomes even stranger when we examine nearby stars. The Sun does not simply orbit the galactic center while maintaining fixed neighbors. The surrounding stars move as well. Some travel faster, others slower. Some rise above the galactic plane, others dive below it. The local stellar neighborhood behaves like a swarm rather than a rigid structure. Stars pass each other over millions of years. Constellations slowly change shape. The night sky humans see today is temporary. Given enough time, familiar patterns will disappear. Orion will distort. The Big Dipper will stretch apart. New patterns will emerge. Future civilizations may inherit a completely different sky. Even the nearest stars participate in this motion. Alpha Centauri, our closest stellar neighbor, is moving through the galaxy. Barnard's star is moving. Sirius is moving. Every star follows its own path through the Milky Way. The galaxy resembles a vast cosmic dance in which billions of stars follow gravitational rules established over billions of years. No participant remains still. As astronomers measured these motions, they realized something profound. The universe is far more active than it appears. The stillness we experience is largely an illusion created by human timescales. A mountain seems permanent because human lives are short. A continent seems fixed because tectonic plates move slowly. The night sky seems stable because stars require centuries to reveal noticeable changes. But given enough time, everything shifts, everything evolves, everything moves. The cosmos is not a frozen structure. It is a constantly changing system operating on timescales far beyond ordinary experience. And yet, astonishingly, even the Sun's journey around the Milky Way is not the end of the story. The galaxy itself is moving. The enormous spiral structure containing hundreds of billions of stars is traveling through space. It interacts gravitationally with neighboring galaxies. It responds to larger cosmic structures. The Milky Way is not anchored. It is part of an even greater journey. Once again, the scale expands. Once again, the speed increases. And once again, the question becomes larger. If Earth moves around the Sun, and the Sun moves around the Milky Way, then where is the Milky Way itself going? The answer takes us beyond the scale of stars and into the motion of entire galaxies, where the true speed of our cosmic journey becomes almost impossible to imagine. The Milky Way does not move through the universe alone. Our galaxy belongs to a small gravitational family known as the local group. This collection contains dozens of galaxies. Most are small, faint dwarf galaxies. A few are much larger. The Milky Way is one of the dominant members. Andromeda is another. The Triangulum galaxy is smaller than both, but still contains billions of stars. Together, these galaxies move through space while pulling on one another. This means the motion of the Milky Way cannot be understood as a simple journey in one direction. Our galaxy is rotating internally. The Sun is orbiting its center. The entire Milky Way is interacting with nearby galaxies, and the local group itself is traveling through the larger universe. Each layer of motion is added to the others. The result is not a clean path. It is a complicated combination of rotations, orbits, gravitational falls, and cosmic expansion. Andromeda provides the clearest example. It lies roughly 2.5 million light-years away. That distance is enormous, but in galactic terms, Andromeda is one of our nearest major neighbors. Unlike most distant galaxies, it is not moving away from us because of cosmic expansion. It is approaching. The Milky Way and Andromeda are being pulled together by their mutual gravity. The distance between them is slowly decreasing. Andromeda approaches at a speed of roughly 100 kilometers per second relative to our galaxy, though its full motion also includes sideways movement. This does not mean the galaxies will collide tomorrow. The journey will take billions of years, but the interaction is already part of our motion. Every person on Earth is traveling with the Milky Way toward a future encounter with another galaxy. The word collision sounds violent. It suggests stars crashing into stars and planets being destroyed instantly. But galaxies are mostly empty space. Even in the crowded regions of a galaxy, stars are separated by enormous distances. When the Milky Way and Andromeda begin passing through each other, direct stellar collisions will probably be rare. The greater danger comes from gravity. As the galaxies approach, their shapes will distort. Spiral arms may stretch. Long streams of stars may be pulled into space. Gas clouds can collide and compress. New stars may form. Some stellar systems may be thrown into new orbits. Others could be moved farther from the galactic center. The two central black holes may eventually approach each other and merge. The galaxies could pass through one another more than once before settling into a larger combined structure. This future galaxy may no longer possess the familiar spiral shape of either parent. It could become a broad elliptical system filled with aging stars. Earth may not exist by then. The Sun will have changed significantly. But our galaxy is already moving toward this future. The path of the Milky Way is partly a path toward Andromeda. Andromeda, however, is also moving. The two galaxies do not approach through a motionless background. Both travel with the local group. Both respond to structures beyond it. To understand the next layer, we must step outside the local group. From far away, the Milky Way, Andromeda, Triangulum, and their smaller companions would appear as a loose island of galaxies. Gravity holds them together strongly enough that cosmic expansion does not pull them apart. The local group is therefore a bound system. Its members may orbit, interact, merge, and rearrange themselves, but they remain connected. The local group is itself located near a much larger collection of galaxies, known as the Virgo cluster. The Virgo cluster contains hundreds, perhaps thousands of galaxies. It lies tens of millions of light years away. Compared with the local group, it is enormous. Its total mass creates a powerful gravitational influence across the surrounding region. For many years, astronomers described the Milky Way and nearby galaxies as moving generally toward Virgo. This motion is real, but the complete story is more complicated. The local group is not simply falling directly into the Virgo cluster. The gravitational landscape around us contains many concentrations of matter. Some are visible as galaxies and clusters. Others are revealed mainly through how they affect motion. The universe on large scales resembles a web. Galaxies gather into groups. Groups gather into clusters. Clusters align along long filaments. Between them lie enormous voids containing far fewer galaxies. Gravity pulls matter away from emptier regions and toward denser ones. The Milky Way's motion is shaped by both. We are attracted toward concentrations of matter. At the same time, the lack of matter inside nearby voids creates an apparent push away from those regions. Nothing inside the void needs to repel us. The surrounding gravity is simply unbalanced. More mass exists on one side than the other. This influences the local group's path. Imagine standing in a landscape surrounded by hills and valleys. A ball will roll according to the shape of the ground. It may be pulled toward one valley while moving away from a high region. On cosmic scales, gravity creates an invisible landscape. Galaxies follow its slopes. The local group is moving through this gravitational terrain. One of the most famous features influencing our region is known as the Great Attractor. The name creates images of a single enormous object pulling galaxies toward it, perhaps a hidden black hole, perhaps an unknown structure beyond the Milky Way. But the Great Attractor is not one isolated object. It describes a region where a large concentration of mass causes galaxies across a vast area to move in a similar direction. The region lies hundreds of millions of light years away, in a part of the sky that is difficult to observe directly. Our own galaxy blocks the view. Gas, dust, and countless stars inside the Milky Way create what astronomers call the zone of avoidance. Visible light telescopes struggle to see through it. A large part of the distant universe is hidden behind our own galactic disk. This is one of the strange limitations of our position. The Milky Way gives us a home, but it also blocks part of the sky. Astronomers must use radio waves, infrared light, X-rays, and other methods to look through the dust. These observations reveal galaxies and clusters hidden behind the galactic plane. The Great Attractor region includes massive structures such as the Norma cluster. It contains an enormous amount of matter. But even this region may not be the final destination of the local group's motion. Beyond it lies an even larger concentration, known as the Shapley supercluster. The Shapley concentration contains many galaxy clusters packed into a relatively dense area. Its gravity may contribute significantly to the motion of our galactic neighborhood. The local group's journey is therefore influenced by structures at several distances. Nearby groups: the Virgo cluster, the Great Attractor region, the Shapley concentration, and the distribution of matter across an even wider volume. There is no single cosmic object pulling everything toward one point. Instead, we are responding to an entire landscape of mass. This is why the question, "Where are we going?" has no simple answer. At one scale, Earth is moving eastward because of rotation. At another, it is moving around the Sun. The Sun moves through the local stellar neighborhood. The solar system orbits the center of the Milky Way. The Milky Way moves toward Andromeda. The local group travels through the cosmic web toward regions of greater density. Each answer is correct. None is complete by itself. To measure the motion of the local group more accurately, astronomers needed a reference larger than nearby galaxies. They found one in the oldest light of the universe, the cosmic microwave background. This faint radiation fills space in every direction. It comes from a time hundreds of thousands of years after the beginning of cosmic expansion, when the universe cooled enough for light to travel freely. Today, the radiation has been stretched into microwave wavelengths. It is almost uniform across the sky. Almost. When astronomers measure it carefully, one side of the sky appears slightly warmer. The opposite side appears slightly cooler. This difference is caused largely by our motion. As the local group moves through the universe, we travel slightly toward the radiation coming from one direction and away from the radiation coming from the opposite direction. The light ahead becomes compressed to slightly shorter wavelengths. The light behind becomes stretched to slightly longer wavelengths. This creates a dipole pattern. By studying it, scientists can estimate our motion relative to the cosmic microwave background. The solar system moves at hundreds of kilometers per second relative to this ancient radiation. Depending on the reference being considered, the local group's speed is also measured at roughly several hundred kilometers per second. This is the closest astronomy comes to providing a broad cosmic reference frame. It does not mean the microwave background is absolutely stationary in a philosophical sense, but it gives us a useful frame in which the ancient radiation appears nearly uniform. Relative to that frame, our galactic neighborhood is clearly moving. The speed is extraordinary, hundreds of kilometers every second, thousands of times faster than a highway vehicle, far faster than any ordinary aircraft. In a single second, the local group crosses a distance comparable to the separation between cities. In 1 minute, it travels tens of thousands of kilometers. During an average human lifetime, our galactic neighborhood moves an enormous distance through the wider universe. And still, compared with cosmic structure, the change is tiny. A galaxy cluster may span millions of light years. A filament may stretch across hundreds of millions, even moving at hundreds of kilometers per second. Crossing these distances would require periods longer than human civilization has existed. This creates a strange contrast. Our speed is tremendous. Our progress is almost invisible. The universe is so large that even extreme motion can appear slow. A similar contrast exists in the Sun's orbit around the Milky Way. More than 800,000 kilometers per hour sounds unimaginably fast. Yet one galactic orbit requires hundreds of millions of years. The scale of the path overwhelms the speed. The local group's movement follows the same principle. We travel quickly. But the structures guiding us are so vast that the journey unfolds across billions of years. The motion is also not perfectly smooth. Galaxies pull on one another. Clusters interact. Dark matter contributes gravity. Gas moves through intergalactic space. Large-scale structures continue evolving. The path of the local group can change over cosmic time. A region that strongly influences us today may merge into another structure later. The Milky Way and Andromeda will combine. The local group may gradually become one dominant galaxy surrounded by smaller remnants. Over much longer times, this merged system may remain gravitationally bound, while distant galaxies move away because of cosmic expansion. This introduces another layer of motion, the expansion of the universe. When astronomers observe distant galaxies, most appear to be moving away from us. The farther they are, the faster their recession tends to be. At first, this might suggest that the Milky Way occupies the center of a gigantic explosion, but that interpretation is incorrect. The galaxies are not simply flying away from one central point through pre-existing space. Space itself is expanding. Every large-scale region sees distant, unbound galaxies receding. An observer in another galaxy would also see the Milky Way moving away. An observer much farther away would see the same broad pattern. There is no known central location inside ordinary space from which expansion began. The expansion happened everywhere. A useful analogy is the surface of an inflating balloon. Imagine dots drawn across the surface. As the balloon expands, every dot moves farther from every other dot. No dot on the surface is the center of the expansion. The center of the balloon exists outside the two-dimensional surface, but in the real universe, we do not need to imagine an external direction in the same way. The analogy is imperfect. It simply shows how all distances can increase without one location being the center. Another analogy involves raisins inside rising dough. As the dough expands, the raisins become farther apart. Each raisin sees the others receding. The raisins themselves are not necessarily growing. The space between them is. Galaxies behave somewhat like the raisins. Structures strongly held together by gravity do not expand internally. The Milky Way is not being stretched significantly by cosmic expansion. The solar system is not expanding. Earth is not expanding. The forces holding these systems together are much stronger locally. Expansion becomes important across enormous distances between galaxy groups and clusters that are not gravitationally bound. This means our motion has two different components. There is local motion through space caused by gravity, and there is the expansion of space changing distances between large structures. The Milky Way can move toward Andromeda, while both galaxies participate in a universe where distant systems recede. Nearby gravity can overcome expansion. Farther away, expansion dominates. This is why Andromeda approaches while most distant galaxies move away. It is also why asking for our total speed through the universe becomes difficult. There is no single universal coordinate system measuring all motion in one simple way. Our speed depends on what we compare ourselves with. Relative to Earth's axis, we rotate. Relative to the Sun, we orbit. Relative to the galactic center, we travel around the Milky Way. Relative to the cosmic microwave background, our galactic neighborhood moves at hundreds of kilometers per second. Relative to very distant galaxies, the changing distance also includes the expansion of space. Each measurement belongs to a different frame. None alone represents an absolute speed through a fixed cosmic background. This idea may feel unsatisfying. Human language naturally expects one final number. How fast are we really moving? But nature does not always provide the kind of answer our intuition expects. Speed is relational. A passenger walking toward the front of a moving train has one speed relative to the train and another relative to the ground. The train has another speed relative to Earth's surface. Earth has another relative to the Sun. There is no contradiction. The passenger can possess several correct speeds at once. We do the same. At this moment, your exact motion depends on where you are standing, the time of day, your latitude, Earth's position in its orbit, the Sun's motion through the galaxy, the direction of the Milky Way relative to the cosmic background. Even walking across a room slightly changes your total velocity relative to distant structures. Your personal movement is tiny compared with cosmic motion, but it still adds another layer. The direction matters as well. At some times of the year, Earth's orbital motion points partly in the same direction as the Sun's galactic motion. At other times, it points partly against it. This means Earth's speed relative to the galaxy changes slightly during the year. Our planet accelerates and decelerates relative to certain reference frames as it travels around the Sun. The same happens during Earth's daily rotation. A person on the evening side of the planet may be moving in a slightly different cosmic direction from someone 12 hours later at the same location. We are constantly turning inside larger turns. Rotation within orbit. Orbit within galactic rotation. Galactic motion within the local group. Local motion within the cosmic web. The true path traced by a person through space-time would be extraordinarily complicated. It would not resemble a simple straight line. Imagine recording your location relative to Earth. You may remain in the same room. Relative to the planet, your path is almost stationary. Now plot the same movement relative to the Sun. The room traces part of a wide orbit. Add Earth's rotation, and the path develops daily curves. Now plot it relative to the center of the Milky Way. The entire solar orbit carries the smaller path forward. Now add the motion of the local group. The line becomes part of an even larger journey. There is no scale at which you are truly motionless. Even when sleeping, you trace a path through the universe that will never be repeated. This is because time also moves forward. Earth may return to the same side of the Sun after 1 year, but the solar system has moved through the galaxy. The galaxy has moved through the local group. The local group has moved relative to the cosmic background. The universe has expanded. The apparent return is not a return to the same place. It is a new location with a familiar arrangement. Every year, Earth completes an orbit while traveling with the Sun into a new region of the galaxy. Every day, the planet rotates while moving forward along that orbit. Every second, our position in the cosmos becomes unique. This has an important consequence. There is no path back to an earlier moment. Even if a spacecraft could reverse every physical direction and return to the same coordinates relative to the Sun, the universe around it would have changed. Stars would have moved. Radiation would have traveled onward. Planets would occupy new positions. Time prevents true repetition. Our movement through space is inseparable from movement through time. Physics combines them into space-time. An object does not merely possess a location. It follows a world line, a continuous path through space and time. Your world line began when you began existing. It moves through every location you occupy. It cannot pause completely, because even at rest relative to nearby objects, time continues. This gives cosmic motion a deeper meaning. We are not passengers traveling through space while time watches from outside. We are moving through a four-dimensional universe where space and time are linked. The speed of light defines the relationship between them. When an object moves faster through space, measurements of time and distance change relative to other observers. At ordinary speeds, these differences are too small to notice. At speeds close to light, they become dramatic. This is the foundation of special relativity. Imagine a spacecraft traveling near the speed of light. To people aboard, time passes normally. Clocks tick. Thoughts continue. Life feels ordinary. But observers on Earth measure the spacecraft's clock running more slowly. The travelers also measure distances in the direction of travel as shortened. This is not an illusion caused by faulty instruments. It is part of how space-time works. Different observers, moving relative to one another, divide space and time differently. There is no single universal clock shared perfectly by the cosmos. This makes the question of motion even stranger. Not only can observers disagree about speed, they can also disagree about the time between events and whether distant events occurred simultaneously. Two events that appear simultaneous to one observer may not be simultaneous to another moving observer. At human speeds, the difference is negligible. At cosmic speeds, it matters. Earth's motions are far too slow compared with light for dramatic everyday time dilation. But the effect exists. Clocks on satellites must account for relativity. Their motion and position in Earth's gravity change the rate at which time passes relative to clocks on the ground. Without corrections, navigation systems would quickly become inaccurate. The technology used to determine your position on Earth depends partly on our understanding that time is not absolute. This connects daily life to cosmic motion. A phone locating itself through satellites relies on physics that also describes stars, black holes, and high-speed spacecraft. The universe does not separate the ordinary from the cosmic. The same laws operate everywhere. Gravity also affects time. A clock closer to a massive object runs differently from one farther away. Earth's gravity creates a measurable difference. The Sun creates another. The Milky Way contributes to the gravitational environment. Every person lives inside layers of curved space-time. Again, these effects are usually tiny in daily life, but they reveal that motion and time cannot be treated as separate, simple backgrounds. The universe has structure. Mass curves space-time. Objects follow paths through that curvature. Earth's orbit around the Sun can be understood not as an invisible force pulling the planet through empty space in the old mechanical sense, but as Earth following the geometry created by the Sun's mass. The Sun follows the curved gravitational structure of the Milky Way. The Milky Way responds to the mass distribution of the local group and larger cosmic web. Our journey is shaped by geometry. The planets do not need to know where to go. They follow the paths allowed by space-time. This does not mean their orbits are fixed forever. Gravitational interactions slowly alter them. The Moon is moving away from Earth. The planets affect one another. Stars passing near the solar system can disturb distant comets. The Milky Way's changing gravitational environment may influence objects at the outer edge of the Sun's domain. Motion creates new interactions. The solar system's journey through the galaxy carries it through different regions. Sometimes it passes closer to spiral arms, sometimes through areas containing more gas. Nearby stellar encounters occur over millions of years. The density of the galactic environment changes. Could this movement affect Earth? Possibly, in limited ways. A close passing star could disturb objects in the distant Oort cloud and send comets inward. Movement through denser interstellar clouds might alter the heliosphere. Nearby supernovae could expose Earth to increased radiation. But these events are rare and complicated. There is no simple repeating galactic cycle known to control all major events on Earth. The solar system's path matters, but it should not be treated as a hidden clock predicting every change in life or climate. The galaxy influences us through real physics, not through vague cosmic destiny. Most of the time, the Sun travels through a relatively quiet region. The solar wind creates a protective bubble around the planets. Earth's magnetic field and atmosphere provide additional protection. Life survives inside layers of defense, while the entire system moves through the Milky Way. These protections are not perfect. High-energy particles still reach Earth. Radiation from the Sun affects satellites and electrical systems. Cosmic rays enter the atmosphere. Occasionally, powerful solar storms disturb technology. Our motion through space does not isolate us from the environment. We travel through a universe filled with particles and fields. Interplanetary space contains the solar wind. Interstellar space contains thin gas, dust, magnetic fields, and cosmic rays. Intergalactic space contains even less ordinary matter, but it is not absolute nothingness. The cosmic microwave background fills it. Neutrinos pass through it. Dark matter contributes gravity. Dark energy influences expansion. Space that appears empty can still contain physical activity. As the Milky Way moves, it interacts with its surroundings. Our galaxy is surrounded by a halo of hot gas. Material flows inward. Other material may be expelled by supernovae and black hole activity. Small galaxies pass through the halo and lose gas. Streams of stars reveal past mergers. The Milky Way is not a rigid ship moving intact through a vacuum. It exchanges matter with its environment. It grows. It changes. It absorbs smaller systems. Our motion belongs to an evolving object. The Sun itself has completed many orbits around the galactic center since forming. Each orbit is sometimes called a galactic year. The solar system is about 4.5 billion years old. This means the Sun has completed only around 20 galactic orbits, perhaps slightly more or less depending on the exact orbital period. 20 journeys. That is all. Earth feels ancient. Its oceans and rocks preserve billions of years. Yet in galactic terms, our solar system has circled the Milky Way only a few dozen times. During one orbit, continents can form and disappear. Species can evolve and vanish. The galaxy changes around us. The Sun does not return to an identical environment after completing a circuit. It travels through a disk whose stars and gas are also moving. The idea of a perfect closed galactic orbit is an approximation. The spiral pattern changes. The gravitational influence of neighboring systems changes. The Milky Way evolves. The orbit may shift. Again, nature refuses to repeat exactly. Our journey is a spiral through time, not a circle returning to a permanent starting point. The Milky Way itself has traveled an enormous distance since the Sun formed. The local group has moved. The cosmic web has evolved. The universe has expanded significantly. When Earth was young, distant galaxies were closer together. The observable universe looked different. Star formation was more active. The expansion rate evolved. Our current speed cannot be separated from this history. Motion occurs inside a universe whose scale changes over time. dark energy adds the most mysterious element. Observations show that cosmic expansion is accelerating. The distances between widely separated unbound galaxies are increasing at an increasing rate. The cause remains unknown. The term dark energy describes whatever is responsible, but naming it does not explain its nature. It may be a property of empty space. It may involve a field. It may reveal that our understanding of gravity is incomplete on the largest scales. Whatever the explanation, the result shapes the future of motion. Distant galaxy groups will continue moving away. Over immense time, many will cross beyond our observable horizon. Their light will become increasingly redshifted and faint. Future observers inside the merged Milky Way Andromeda galaxy may see far fewer external galaxies. The universe will appear emptier. If they have no ancient records, discovering cosmic expansion may become far more difficult. Our current era is special in one practical sense. We can still observe enough of the universe to reconstruct its large-scale history. The cosmic microwave background remains detectable. Distant galaxies remain visible. Expansion can be measured. Billions or trillions of years from now, much of this evidence may fade from local observation. Cosmic motion changes what can be known. The local group will not be carried apart internally because its gravity is strong enough to hold it together. The Milky Way and Andromeda will merge. Nearby dwarf galaxies may eventually join the combined system, but distant clusters will recede. The local region will become an isolated island galaxy, surrounded by expanding darkness. Where are we going? In the near cosmic future, the Milky Way is moving toward Andromeda. The local group is moving through the gravitational landscape of nearby large-scale structure. Over longer times, its members will merge into one system. That system will remain isolated while the wider universe expands beyond reach. Our destination is therefore not one fixed point. It is a sequence of transformations, a future galactic merger, a rearranged stellar population, an increasingly isolated local island, and eventually a universe in which visible motion occurs mainly within the structure that remains gravitationally bound. The concept of destination may not even apply. Galaxies do not travel toward a final station. They follow gravity while space-time evolves. The journey never pauses to announce arrival. One configuration becomes another. The Milky Way becomes part of a merged galaxy. Stars die, new stars form. Gas is consumed. Planetary systems change. Black holes grow. Distant structures disappear beyond the horizon. Motion continues, but its appearance changes. This is true for Earth as well. Our planet travels through space without a final destination. Its orbit is not a road leading somewhere else. It is a stable relationship with the Sun. The Sun's galactic orbit is not a voyage toward the center. It is a continuing gravitational path. The local group's movement is not necessarily a journey toward one permanent object. It is the response of matter to surrounding structure. Perhaps the most accurate answer is that we are going into the future. Every motion carries us there. Every rotation, every orbit, every galactic movement. Space changes our position. Time makes the change irreversible. We may ask where Earth will be tomorrow. The answer can be calculated relative to the Sun. We may ask where the Sun will be in 1,000,000 years. The answer can be estimated relative to the galaxy. But ask where everything is going ultimately, and prediction becomes more uncertain. Small gravitational differences grow over long periods. Stars pass near one another. Galaxies merge. Dark energy changes accessible distances. The universe is governed by laws, but complex systems can still be difficult to predict exactly. This uncertainty does not mean nothing can be known. It means cosmic motion is richer than one arrow drawn across a diagram. The arrow depends on scale. A diagram showing Earth's orbit hides galactic motion. A diagram showing the Milky Way's path hides internal rotation. A map of the local group hides the expansion of distant space. Every simple picture leaves something out. To understand our journey, we must hold several pictures at once. Right now, Earth rotates. It carries you around its axis. At the same moment, Earth moves around the Sun. The Sun carries the entire planetary system around the Milky Way. The Milky Way moves relative to Andromeda and nearby galaxies. The local group travels relative to the cosmic microwave background. The surrounding universe expands. These motions do not cancel one another. They combine into the path you are following now. And yet your cup remains on the table. Buildings stand. Oceans stay on Earth. You do not feel a cosmic wind against your face. This is because constant velocity is not felt directly. We feel acceleration. A car seems motionless while traveling smoothly at constant speed. We notice when it turns, stops, or accelerates. Earth's rotational and orbital motions involve acceleration because their directions continuously change. But the forces involved act on us and our surroundings together. Gravity holds us to the planet. The ground supports us. The atmosphere shares Earth's motion. The accelerations are either gentle enough or constant enough that they become part of ordinary experience. Your body developed inside these conditions. You do not experience Earth's gravity as a strange cosmic force. You experience it as weight. You do not experience rotation as a continuous dramatic event. You experience the cycle of day and night. You do not experience orbit as falling around the Sun. You experience a year. Cosmic motion is translated into the rhythms of life. Days are rotation, years are orbit. Seasons result from Earth's tilted axis maintaining its orientation as the planet travels around the Sun. The night sky changes because Earth moves along its path. The motions we cannot feel create the calendar we use to organize existence. Every morning is evidence of rotation. Every birthday is evidence of orbital motion. Every slowly changing constellation is evidence of stellar movement. Every redshifted galaxy is evidence of cosmic expansion. Movement surrounds us so completely that we mistake it for stillness. Only by comparing positions over time does the hidden journey appear. Ancient observers recorded stars. Later generations noticed changes. Telescopes measured planetary paths. Photography revealed stellar motion. Spectroscopy revealed whether objects approached or receded. Radio observations uncovered hidden galaxies. Microwave detectors measured our motion relative to ancient radiation. Humanity built a picture of movement from layers of evidence. No single person could feel the answer. We had to measure it. This is one of science's greatest strengths. Our senses are valuable, but limited. They evolved to help us move through landscapes, recognize danger, find food, and communicate. They were not designed to detect galactic rotation or cosmic expansion. Instruments extend perception. A telescope turns faint light into structure. A spectrograph turns color into speed. A radio antenna detects signals invisible to the eye. A spacecraft measures environments no person can reach. Mathematics connects the observations. Through these tools, a stationary observer on Earth can discover that the ground beneath them is moving at extraordinary speed. And the discovery does not make ordinary life less real. The table remains solid. The room remains quiet. It simply places that quiet moment inside a larger truth. You are not watching the universe from outside. You are participating in its motion. The atoms in your body move with Earth. Earth moves with the sun. The sun moves with the galaxy. The galaxy moves with the local group. The local group moves through the cosmic web. There is no separation between you and the journey. You are part of the object whose speed you are trying to understand. That may be why the motion feels so impossible. There is no nearby platform standing outside the universe from which we can observe our total path. Every possible observer also moves. Every measurement must compare one moving system with another. We can define useful reference frames: the ground, the sun, the galactic center, the cosmic microwave background. But we cannot step completely outside reality and ask how fast the whole universe is moving through something beyond itself. The universe may not be moving as one object through a larger external space at all. Expansion happens internally. Distances change within space-time. Asking for the speed of the entire universe may have no physical meaning. The universe is not necessarily a spacecraft traveling through a surrounding void. It includes the space in which motion is defined. This is where the simple question becomes profound. How fast are we really moving? The answer begins with numbers. Earth rotates at up to roughly 1,670 kilometers per hour at the equator. Earth orbits the sun at around 107,000 kilometers per hour. The sun travels around the Milky Way at hundreds of thousands of kilometers per hour. Our galactic neighborhood moves relative to the cosmic microwave background at hundreds of kilometers per second. But the final answer is not one larger number produced by simply adding everything together. The directions differ. The frames differ. The motions change over time. The expansion of space does not behave like ordinary motion through space. The honest answer is a collection of speeds, each describing one relationship, and together they reveal something far more interesting than a single number. We live inside a universe with no universal stillness. Every scale moves, planets rotate, moons orbit, stars travel, galaxies collide, clusters fall along filaments. Space expands between distant structures. Nothing remains completely fixed. The stillness around you is local and temporary, a shared motion mistaken for rest. Tonight, while you lie quietly, Earth will turn. Your location will sweep through thousands of kilometers. The planet will advance along its orbit. The sun will continue around the Milky Way. The local group will move through ancient radiation and toward the mass concentrations shaping its path. By morning, you will occupy a region of the universe you have never occupied before. You will never return to the exact place you are leaving now. The journey continues without engines, without sound, without a destination visible ahead. And we have still explored only the motion that can be measured through nearby matter and cosmic light. The next question is even more difficult. If everything moves relative to something else, could there be any true center of the universe? Is the Milky Way moving away from a beginning? Are we traveling toward an edge? Or do the words center and edge fail when applied to the universe as a whole? To answer that, we must stop following individual objects and examine the geometry of the cosmos itself, because knowing our speed is only part of the mystery. We must also understand what kind of universe allows all of this motion to exist. The search for our cosmic destination becomes much more difficult when we ask whether the universe has a center. Everything in ordinary life seems to have one. A city has a central district, a planet has a core, a solar system has a dominant star, a galaxy has a central region. Even a storm can have an eye around which the atmosphere rotates. So it feels natural to assume that the universe must also possess a central point, perhaps a place from which everything began, perhaps a location toward which all motion can ultimately be measured. If such a center existed, then the direction of our journey might finally become clear. We could determine whether the Milky Way was moving toward it, away from it, or around it. But modern cosmology suggests that the universe does not contain a center in the ordinary sense. The beginning was not an explosion occurring at one location inside a larger empty space. It was an early state in which the entire observable universe was far hotter and denser than it is today. Space did not expand outward from one central point into a surrounding void. Distances increased everywhere. Every sufficiently separated region moved away from every other region as the universe expanded. This means the beginning happened here. It also happened in the region now occupied by Andromeda. It happened within the material that became distant galaxy clusters. Every part of the present universe emerged from that earlier dense condition. There is no direction in the sky that points toward the place where the Big Bang occurred. Looking in any direction allows us to see increasingly ancient light. Every line of sight leads backward toward the young universe. If we look toward one side of the sky, we see cosmic history. If we turn around, we see the same broad sequence in the opposite direction. The oldest radiation surrounds us because the early universe existed everywhere, not because Earth sits at the center of a spherical explosion. This is one of the hardest ideas to visualize. Human intuition is built around objects expanding into something around them. A firework explodes into air. A wave spreads across water. A cloud expands through the atmosphere. But cosmic expansion does not require an external space into which the universe grows. It describes how distances behave within the universe itself. The geometry changes. Widely separated points become farther apart. The universe does not need an outer room. And if there is no central point inside ordinary space, then our motion cannot be described as a journey away from the center of creation. The Milky Way is not being launched outward from a cosmic origin located behind us. It is moving locally through the gravitational structure surrounding it, while the larger distances between unbound regions change. This distinction separates two types of motion that can appear similar from a distance. The first is peculiar motion. This is the movement of an object relative to the general cosmic expansion. The Milky Way's motion toward Andromeda is peculiar motion. The movement of the local group relative to nearby galaxy concentrations is peculiar motion. The orbit of the Sun within the Milky Way is also local motion caused by gravity. The second type is recession caused by expansion. A sufficiently distant galaxy may become farther away even if it is not racing through local space in the ordinary sense. The space between us and that galaxy grows. Astronomers separate these effects when interpreting observations. A nearby galaxy can possess a peculiar velocity large enough to move toward us despite expansion. A distant galaxy's local motion may point toward us, but the growing distance between our regions can still carry it away overall. At the scale of galaxy clusters, gravity and expansion compete. Inside a bound cluster, gravity wins. The galaxies remain connected. Between widely separated clusters, expansion usually dominates. This creates a universe with countless local centers of motion, but no single universal center. Earth orbits the Sun. The Sun orbits the Milky Way. Stars near the galactic core orbit a shared concentration of mass. Galaxies within clusters move around complex gravitational centers. But none of these local centers is the center of the entire universe. They are temporary centers created by matter gathering under gravity. Another common question follows. If the universe has no center, does it have an edge? Could the Milky Way be traveling toward a boundary? Perhaps an outer surface separating the universe from something beyond it? Again, the answer may not resemble ordinary experience. The observable universe has a limit, but that limit is not necessarily a physical edge. It is a horizon. Light travels at a finite speed. The universe has existed for a finite amount of time. Only signals from a certain range have had enough time to reach us. More distant regions may exist, but their light has not arrived. The observable universe is therefore centered on the observer. Someone in another galaxy possesses a different observable region. Their horizon surrounds them. Some of what they can see overlaps with what we can see. Other regions may lie beyond our present view. This does not make every observer the physical center of reality. It makes every observer the center of their own information horizon. A ship on a calm ocean sees a circular horizon. Moving the ship moves the horizon. The visible boundary is not the edge of the ocean. It is the limit imposed by the observer's position and the curvature of the surface. The cosmic horizon is far more complicated, but the basic lesson is similar. The boundary of visibility is not automatically the boundary of existence. The universe may extend far beyond the region accessible to our telescopes. It could be finite, but much larger than we can observe. It could be infinite. Current measurements suggest that space is extremely close to geometrically flat on large scales, but flatness does not prove infinity. A large curved space could appear nearly flat within the portion available to us, just as a small section of Earth appears flat from the ground. If the universe were finite and curved in certain ways, it might possess no edge at all. Traveling far enough in one direction could theoretically return a traveler to the starting region, depending on the topology of space. This would be similar to traveling around Earth without encountering a boundary. The surface is finite, yet there is no edge where the ground ends. A three-dimensional universe could possess an analogous structure that is difficult to imagine, because our minds are accustomed to embedding curved surfaces inside a higher dimensional environment. Mathematics can describe such possibilities even when visualization fails. If space is infinite, then there is no final galaxy and no outer boundary. The cosmic web may continue beyond the observable horizon, not necessarily with the exact same arrangement, but perhaps with the same broad laws and statistical patterns. In that case, asking where the Milky Way is traveling relative to the edge would be meaningless. There would be no edge. We would be moving through one local region of an endless cosmos. If space is finite but unbounded, the question would still be misleading. There might be no boundary toward which anything travels. The universe could be limited in total volume, while allowing motion in every direction without meeting a wall. Either possibility removes the simple image of the Milky Way racing toward the outer rim of existence. Our destination must therefore be described through the structures that actually influence us. Gravity provides the clearest guide. The Milky Way and Andromeda are approaching because they occupy the same gravitationally bound group. Their future encounter will reshape the local environment. The merged galaxy will probably be larger and less organized than either spiral appears today. Its stars will settle into new paths. The Sun, if it still exists in its present stage, could be moved into a more distant region. The solar system might pass near other stars during the changing gravitational conditions, though a close destructive encounter remains unlikely because interstellar distances are so large. The night sky would transform over millions of years. Andromeda would grow from a faint blur into a vast luminous structure. Its spiral disk would stretch across the darkness. Individual regions of star formation could become visible. As the galaxies passed through each other, long arcs of stars might surround the sky. The central regions would brighten. Gas compressed by the encounter could ignite waves of new star formation. For any observers still living in the system, the heavens would no longer resemble the quiet sky known to humanity. But even this dramatic event would not represent an ultimate destination. After the merger, motion would continue. Stars would orbit the combined center. Smaller galaxies would be absorbed. Gas would gradually be consumed or expelled. The new galaxy would age. The remaining members of the local group would continue responding to its gravity. Over extremely long periods, the group might settle into one dominant island of stars. Beyond it, cosmic expansion would carry unbound galaxy clusters farther away. Their light would stretch, their images would fade. The cosmic web visible today would slowly disappear from local observation. This future isolation does not mean our galaxy will stop moving. It means fewer distant structures will remain accessible as useful references. Motion inside the merged system will continue. Stars will pass through their orbits. Planetary systems will travel around the galactic center. Black holes will interact. Stellar remnants will drift. But the wider universe will become increasingly hidden. Our present ability to measure a broad cosmic reference depends on ancient radiation and visible distant galaxies. Far future observers may face a very different scientific environment. The cosmic microwave background will continue to stretch toward longer wavelengths. Its temperature will decrease. Eventually, it may become extremely difficult to detect against local effects. Distant galaxies will move beyond the cosmic event horizon. Their light emitted in the far future will never reach the local group. The evidence that the universe once contained a rich network of external galaxies may survive only in records. If those records are lost, a civilization arising in the remote future could believe that its galaxy is all that exists. Its telescopes might reveal only local stars and darkness. The expansion that now helps us understand cosmic history could hide its own evidence. This future gives the question of motion a tragic quality. We are not only moving through the universe. The visible universe is changing around us. Some information is arriving for the first time. Other information is fading forever. Light from distant sources enters our horizon, while accelerated expansion limits what can reach us in the future. Astronomy is possible because we exist during a period when many layers of cosmic history remain observable. Our motion through time determines the universe available to knowledge. Yet even now, we cannot measure our journey from an external viewpoint. There is no camera outside the universe showing the Milky Way's full path. Astronomers reconstruct motion from relationships. The spectrum of a star reveals whether it approaches or recedes. The position of a star measured across years reveals sideways movement. The microwave background reveals our motion relative to ancient radiation. Galaxy surveys map flows toward concentrations of mass. Gravitational lensing exposes invisible matter. Every measurement is local evidence assembled into a larger model. One particularly useful concept is the solar apex. As the sun moves relative to nearby stars, there is a direction in the sky toward which it appears to travel. Stars in that direction show a pattern consistent with our approach. Stars behind us show the opposite pattern. This does not mark the ultimate destination of the solar system. It describes the sun's motion relative to a selected group of nearby stars. Change the reference population, and the measured direction changes slightly. Nearby stars themselves possess different velocities. Some belong to the thin disk of the Milky Way. Others move through the thicker stellar disk. Some are members of the halo, following highly inclined paths around the galaxy. The Milky Way is made from overlapping populations with different histories. The sun travels within this mixture. Astronomers define a local standard of rest to describe an idealized average motion of material near the sun around the galactic center. The sun has a small additional velocity relative to that local average. This is another reminder that no single number describes all movement. The sun orbits with the disk, but it also moves slightly inward or outward, upward or downward, and faster or slower than neighboring averages. Its path around the Milky Way is not a flat, perfect circle. The solar system moves vertically through the galactic disk. It rises above the central plane. Then, gravity pulls it back. It passes through the plane and continues to the opposite side. The motion resembles a gentle oscillation superimposed on the much larger galactic orbit. Over tens of millions of years, the sun moves up and down relative to the disk. At the same time, its radial distance from the galactic center can change slightly. The orbit is a complex path through a changing gravitational field. The sun may also have formed at a different distance from the center than the one it occupies now. Interactions with spiral patterns and other structures can cause stars to migrate through the disk over billions of years. Our solar system may have moved significantly from its birthplace. The atoms that became Earth gathered inside a stellar nursery that no longer exists as a recognizable structure. The sun's sibling stars, born from the same cloud, were scattered throughout the galaxy. Some may now lie thousands of light years away. We do not know all of them. The solar system has been separated from its original family by galactic motion. This gives our journey a hidden history. Before Earth formed, earlier stars created the heavy elements needed for the planets. Their material mixed inside a molecular cloud. That cloud moved through the Milky Way. Part of it collapsed. The sun formed. The surrounding disk became planets, moons, asteroids, and comets. Then the newborn stellar group dispersed. The sun began its independent path through the galaxy. Every orbit since then has carried Earth through new surroundings. The galaxy experienced mergers. Stars formed and died. Spiral patterns changed. The solar system survived, while its birthplace vanished into the wider disk. Our direction of travel today is therefore not a continuation along a permanent road. The galactic landscape itself evolves. A spiral arm is not a solid tunnel that the sun follows forever. It is a pattern moving through the disk. Gas enters it. Stars form. Material passes through. The sun's relation to these patterns changes over time. Future maps of the Milky Way will not match present maps exactly. The central bar may evolve. Spiral arms may strengthen, weaken, split, or reconnect. Satellite galaxies may disturb the disk. The coming interaction with Andromeda will eventually erase much of the current structure. Where we are going depends partly on a destination that is being transformed before we arrive. This resembles traveling across a river while the current reshapes both banks. There is motion of the traveler and motion of the environment. The two cannot be separated completely. Dark matter adds another hidden layer. The visible disk of the Milky Way occupies only part of the galaxy's gravitational structure. A vast halo of dark matter surrounds it. We cannot see this material directly. It does not appear to absorb, emit, or reflect ordinary light in the usual way. But its gravity affects the speeds of stars and gas. Without the halo, the outer parts of galaxies would not rotate as observed. The solar system therefore moves not only through a landscape created by stars, it moves through a larger invisible mass distribution. Dark matter particles, assuming they exist as many theories suggest, may pass through Earth continuously. They could move through buildings, oceans, rock, and living bodies with almost no interaction other than gravity. Experiments deep underground search for rare collisions between dark matter and ordinary atoms. So far, the nature of dark matter remains unknown, but its presence influences our galactic path. The Milky Way's dark halo interacts gravitationally with Andromeda's halo long before their visible disks meet. The merger has already begun in the broadest sense, because the outer halos may extend far enough to overlap or approach one another. The galaxies appear separated in visible light. Their invisible environments reach much farther. This changes the image of our future encounter. It is not two bright disks suddenly colliding in empty space. It is a slow gravitational interaction, beginning across vast diffuse halos. The visible stars respond later. Long before the famous spiral shapes distort, dark matter and sparse outer material participate in the approach. The local group's motion through the broader cosmic web is also largely guided by dark matter. Galaxies trace concentrations of mass, but they reveal only part of it. The largest structures formed around invisible frameworks established early in cosmic history. Dark matter gathered into filaments and halos. Ordinary gas fell into those gravitational wells. Stars and galaxies formed inside them. The luminous cosmic web is therefore a visible coating on a much larger invisible structure. When we say the local group moves toward a dense region, much of the attracting mass may not shine. We follow gravity whose source is only partly visible. This makes our motion feel even more mysterious. We can map the path. We can measure the acceleration. We can estimate the mass. But the dominant material shaping that movement remains unidentified. The universe is carrying us through a structure made largely from something we do not understand. The same is true of cosmic expansion. Dark energy appears to dominate the universe's large-scale energy budget. It determines the future separation of distant galaxies. Yet we do not know what it is. Our local path is shaped mainly by dark matter and ordinary matter. Our most distant future is shaped strongly by dark energy. The universe's motion is governed by two invisible components whose fundamental nature remains unknown. Ordinary matter, everything made from atoms, forms stars, planets, life, and telescopes, but it represents only a minority of the cosmos. The visible universe explains neither all gravity nor all expansion. Our journey is therefore guided mostly by unseen influences. If dark energy remains constant, accelerated expansion will continue. Galaxy groups not bound to us will eventually become unreachable. If dark energy changes over time, the future could be different. Expansion might weaken, it might strengthen. In extreme speculative models, it could grow powerful enough to disrupt galaxies, solar systems, planets, and eventually matter itself. This hypothetical outcome is sometimes called the Big Rip. There is currently no evidence that such an ending is inevitable. It depends on properties of dark energy that remain uncertain. Another possibility is that expansion continues forever at an accelerating rate while bound structures survive. Stars gradually exhaust their fuel. Galaxies grow dark. Stellar remnants dominate. Black holes eventually become the most significant large objects. Over unimaginable durations, even black holes may lose energy through quantum processes. The universe approaches a state of increasing cold and emptiness. Motion does not cease completely, but useful differences in energy become rarer. This long-term possibility is often associated with heat death. It is not an explosion or a final collision. It is the gradual fading of organized activity. If this is the future, then our destination is not a place. It is a changing physical condition. The Milky Way moves toward Andromeda in the relatively near cosmic future. The merged galaxy moves through an expanding universe. Its stars age, its structure transforms. Its visible environment becomes isolated. Eventually, the pathways available to matter and energy become increasingly limited. The journey continues even when familiar landmarks disappear. There are other proposed cosmic futures. If dark energy were temporary and gravity eventually overcame expansion, the universe could contract. Distant structures would stop receding. Matter would move closer. Temperatures would rise. A final collapse might occur. Present evidence does not favor this outcome under the simplest models, but cosmology remains dependent on measurements and assumptions about components we do not fully understand. Some ideas suggest cycles of expansion and contraction. Others propose changes in the vacuum state of space. A transition to a lower energy state could spread at nearly the speed of light, changing the laws experienced by matter. Such possibilities are highly speculative. They remind us that predicting the ultimate destination of everything requires physics beyond our current certainty. We can describe the coming galactic merger with reasonable confidence. We can model the expansion of the near future. But the farther forward we look, the more uncertainty grows. Even the Sun's future illustrates this. We know it will continue converting hydrogen into helium in its core. Its brightness will slowly increase. In roughly 1 billion years, Earth's climate may become far more hostile as solar luminosity rises. Several billion years later, the Sun will expand into a red giant. The inner solar system will be transformed. Mercury and Venus will almost certainly be engulfed. Earth's fate is less certain in detail, but it will no longer remain the world we know. The Sun will then shed its outer layers. A white dwarf will remain. The planetary system, if any bodies survive, will continue orbiting a small, dense stellar remnant. All of this will occur while the Milky Way and Andromeda interact. The solar system's future cannot be separated from galactic evolution. A red giant sun may shine inside a galaxy already changing shape. The planets may experience altered stellar encounters as orbits reorganize. The final white dwarf may travel through a merged galactic environment very different from the Milky Way seen today. Our familiar cosmic address will vanish. There will be no Earth in its present form. No recognizable solar system, no Milky Way spiral. But the material will continue. Atoms from Earth may enter the Sun. Others may be scattered by impacts or stellar evolution. Some could travel into interstellar space. Human-made spacecraft already follow paths that may outlast our species. Voyager, Pioneer, and other probes will drift between stars after their power ends. They do not move fast enough to escape the Milky Way under ordinary conditions. They will orbit the galactic center along with the stars. Over millions and billions of years, close gravitational encounters could alter their paths. Microscopic impacts will damage their surfaces. Radiation will change their materials. Eventually, they may become unrecognizable. But for a long period, fragments of human technology will participate independently in galactic motion. These spacecraft provide a small physical answer to where humanity is going. Parts of us have already left the planetary environment. They are not heading toward the edge of the universe. They are entering the long gravitational circulation of the galaxy. Their destinations depend on encounters that cannot be predicted over extreme timescales. They may pass near stars. They may wander through dark interstellar regions. They may remain untouched for ages. Their journey is not guided by engines anymore. It is guided by inertia and gravity. Every object follows this principle. Once a spacecraft finishes accelerating, it does not need continuous thrust to keep moving through empty space. It continues along its path unless forces change that path. The planets do not require engines to remain in orbit. Their motion and gravity create a continuous fall. Earth falls toward the sun, but moves sideways quickly enough to keep missing it. The moon falls toward Earth while continuously missing the surface. The sun falls through the gravitational field of the Milky Way while orbiting its center. The local group follows the curved structure created by surrounding mass. The universe is filled with objects falling without arriving. An orbit is a fall transformed into repetition. But even repetition is temporary. Energy can be exchanged. Orbits evolve. External forces intervene. A moon moves outward. A satellite falls inward. A star changes mass. A galaxy encounters another. No orbit is guaranteed forever. This returns us to the idea of destination. In ordinary travel, a destination is where motion ends. Cosmic motion rarely works that way. Earth reaches no final point in its solar orbit. The Sun reaches no station in its galactic path. The Milky Way does not arrive at Andromeda and stop. The encounter creates new motion. The local group does not simply fall into one fixed attractor. Its structure evolves while the universe expands. Every apparent destination becomes a transition. Perhaps the best description is not that we are going somewhere. We are becoming something else. Earth becomes an older world. The sun becomes brighter, then expands, then fades into a remnant. The Milky Way and Andromeda become one galaxy. The local group becomes more isolated. The universe becomes more expanded. Motion carries matter through changing forms. A person listening quietly is also part of this transformation. The body replaces atoms continuously. Cells divide. Memories change. The planet moves. The sky evolves. There is no fixed observer traveling through a fixed universe. Both the observer and the environment change together. This is why finding absolute rest is impossible in more than one sense. There is no universally preferred place where all spatial motion stops. There is also no permanent physical arrangement that remains unchanged while everything else moves around it. Matter evolves. Time continues. Even a perfectly isolated object would age internally. Particles would interact. Quantum states would change. Stillness is never complete. The universe may contain no final center, no reachable edge, and no absolute rest. Yet it is not directionless. Local structures provide meaningful paths. Earth has a measurable direction around the Sun. The Sun has a measurable motion relative to neighboring stars. The local group has a measurable velocity relative to the cosmic microwave background. These directions can be drawn on maps, but each belongs to a chosen scale. Zoom out, and the arrow changes. Zoom farther, and the meaning of motion changes from travel through space to growth of space itself. At the largest scale, galaxies are often described using comoving coordinates. This system imagines a grid that expands with the universe. A galaxy following the average expansion can remain at nearly the same comoving position even while its physical distance from other galaxies grows. The grid stretches. This mathematical viewpoint separates expansion from local motion. It allows cosmologists to map structures across time without pretending that every receding galaxy is moving through static space like a projectile. In ordinary physical coordinates, the distances increase. In comoving coordinates, the large-scale pattern can be compared across different eras. The same object can therefore be stationary in one useful coordinate system and moving in another. This does not create contradiction. Coordinates are tools. They describe relationships. The universe does not label one grid as the only real one. Physics predicts measurable events regardless of the chosen description when the mathematics is used correctly. This flexibility is essential because cosmic scales resist ordinary intuition. Words such as here, now, distance, and speed become dependent on the observer and the geometry. A nearby object has a well-defined distance that can be measured through radar or parallax. A remote galaxy observed billions of light years away can have several meaningful distances. The distance its light traveled, its distance when the light was emitted, its estimated distance now, its comoving distance within the expanding cosmic model. These values are not always the same. Asking how fast the galaxy recedes also requires specifying the definition being used. At great enough distances, the rate at which separation increases can exceed the speed of light. This does not violate relativity because the galaxy is not locally traveling through space past nearby objects faster than light. The space between distant regions is expanding. Relativity prevents matter and information from locally crossing space faster than light. It does not impose the same simple limit on how quickly sufficiently large cosmic distances can grow. This is another reason no single speed can describe our motion through the entire universe. Local velocity obeys one set of comparisons. Cosmic recession involves evolving geometry. Combining them carelessly creates misleading numbers. The most honest answer remains layered. We can say how quickly Earth rotates relative to its axis, how quickly it orbits relative to the Sun, how the Sun moves relative to local stars, how the solar system travels relative to the galactic center, how the local group moves relative to ancient radiation. But asking for our speed relative to space itself assumes that space is a fixed substance with a universal stationary frame. Modern physics does not require such a frame. Experiments searching for absolute motion through a hypothetical medium failed to reveal one. The speed of light behaves consistently for observers in inertial motion, leading to relativity's transformation of space and time. There is no detectable cosmic wind produced simply by uniform motion through empty space. The microwave background provides a natural cosmological frame because its radiation becomes nearly uniform there, but it does not restore an absolute mechanical rest frame required by the laws of physics. A laboratory moving relative to the microwave background still performs local experiments according to the same physical laws. Nothing about life on Earth changes because our galaxy has a cosmic velocity. The reference is useful, not fundamental in the old absolute sense. This subtle distinction matters. We can identify a frame in which the large-scale universe looks especially simple. But physics does not declare every object at rest in that frame more truly stationary than objects moving relative to it. Motion remains relational. The universe provides structure without giving us an absolute platform. So where are we going? Toward tomorrow's position in Earth's orbit, toward a new region of the Sun's galactic path, toward a future encounter between the Milky Way and Andromeda, along the local group's movement through the surrounding gravitational web, into a cosmic era of increasing separation from distant unbound galaxies. These answers exist simultaneously. None reduces the others. The journey is not one arrow. It is a hierarchy of paths nested inside one another. And every path evolves. Tonight, Earth will continue turning while the continents move through darkness and sunlight. The planet will advance millions of kilometers along its orbit before another day passes. The Sun will shift farther along its immense galactic route. Nearby stars will alter their positions by tiny amounts. The Milky Way and Andromeda will become slightly closer. The local group will move through the ancient frame revealed by the microwave background. Distant galaxies will recede. Photons that have traveled for billions of years will finally reach Earth. Other photons leaving those galaxies now may never arrive. Nothing dramatic will be felt. The room will remain quiet. But the geometry of your relationship with the universe will never be exactly the same again. There is no road beneath us, no engine carrying the planet, no destination sign ahead. Only gravity, inertia, expanding space and time. Together, they create the greatest journey imaginable. A journey that began before Earth formed. A journey that will continue after the Sun is gone. And perhaps the strangest truth is that we do not need to leave home to participate. We are already moving. We have always been moving. The universe does not wait for us to begin the voyage. It carries us with it. And as we travel, the deeper mystery is no longer simply how fast we are moving. It is whether movement itself could ever have an end. Could the universe someday become truly still? Could every orbit stop, every galaxy settle, and every particle reach a final state? Or is motion so deeply built into reality that complete stillness has never existed and never will? To answer that, we must look beyond planets and galaxies and examine the smallest particles, the expansion of space-time, and the distant future when nearly every light in the universe has faded. Because our journey may have no final destination, but it may still be carrying everything toward a final kind of universe. Could the universe ever become completely still? At first, the answer seems simple. If every engine stopped, every planet settled, every star exhausted its fuel, and every galaxy ceased interacting, perhaps motion would gradually disappear. The universe would become quiet. Dark, frozen, permanent, but complete stillness may be far more difficult to achieve than it appears. Motion is not only something performed by planets, stars, and galaxies. It exists inside matter itself. The chair beneath you may seem motionless, yet its atoms are constantly active. They vibrate within molecules and crystal structures. Electrons occupy changing quantum states. Particles exchange energy. Light enters and leaves the material. Tiny interactions occur continuously. even though the object appears perfectly still from a human perspective. Temperature is partly a measure of microscopic motion. In a warm object, particles possess more average kinetic energy. They move and vibrate more intensely. As the object cools, this activity decreases. Scientists can create temperatures extremely close to absolute zero, the lowest temperature allowed by ordinary thermodynamics. Near this limit, many forms of thermal motion become incredibly small. Matter can enter unusual states. Atoms may behave collectively. Quantum effects normally hidden by heat become easier to observe. But reaching absolute zero exactly appears impossible through any finite physical process. Cooling removes energy step by step. As temperature approaches the limit, extracting the remaining energy becomes increasingly difficult. The final distance can be approached, but never completed. Even at the lowest possible energy state, quantum physics does not necessarily allow every particle to become perfectly motionless. A particle cannot always possess an exact position and an exact momentum simultaneously. The more precisely one property is defined, the less precisely the other can be known. This is not simply a limitation of measurement equipment. It is built into the mathematical structure of quantum mechanics. A perfectly stationary particle, fixed at one exact location, would violate this relationship. Instead, quantum systems possess unavoidable uncertainty. Even their lowest energy states can contain what is called zero-point energy. This does not mean a hidden source of unlimited usable power. It means that nature may never permit the simple classical stillness we imagine. At the smallest scales, reality is not composed of tiny rigid balls resting in exact positions. It is described through probabilities, fields, interactions, and quantum states. The idea of absolute motionlessness begins to lose meaning. An atom at rest relative to a laboratory still participates in quantum behavior. A laboratory at rest relative to Earth moves with the planet. Earth moves through the solar system. And even if every larger motion could somehow be removed, the internal physical state would not become a perfectly frozen picture. The universe may contain no true pause button. This becomes even clearer when we consider light. A photon cannot be brought to rest in empty space. It always travels at the speed of light locally. It may be absorbed by matter. Its energy may be transferred. Its wavelength may stretch as space expands. But while it exists as a freely traveling photon, motion is part of its nature. The universe is filled with radiation. Starlight, radio waves, microwaves, X-rays. Ancient photons released long before Earth formed. Some travel through space for billions of years before interacting with anything. As long as radiation remains, there is movement. Neutrinos also cross the cosmos. They interact so weakly with ordinary matter that enormous numbers pass through planets and living bodies almost without leaving a trace. They originate in stars, nuclear reactions, supernovae, and the early universe. The room around you may appear empty and still, yet invisible particles are passing through it continuously. Some began their journey inside the sun. Others may have traveled from distant explosions. The apparent stillness of daily life hides an invisible traffic extending across cosmic distances. Gravitational waves add another layer. When massive objects accelerate, they can disturb space-time and send ripples outward. Black holes merge. Neutron stars collide. Asymmetric stellar explosions may create weaker signals. The ripples spread at the speed of light. Long after the event ends, the disturbance continues traveling. Space itself carries evidence of past motion. A collision in a distant galaxy can create a change so small that detectors on Earth must measure lengths with extraordinary precision to find it. The signal passes, space-time settles locally, but the wave continues beyond us. The universe is filled with messages from motion that occurred elsewhere and long ago. Even when the source becomes quiet, its influence keeps moving. This means that stopping every visible object would not immediately create stillness. Radiation would continue crossing space. Gravitational waves would continue spreading. Particles would continue moving. Fields would continue existing. And the geometry of the universe might continue changing. Cosmic expansion does not require galaxies to fire engines. It is part of the large-scale evolution of space-time. According to current observations, expansion is accelerating. Distant, unbound structures become increasingly separated. Their light is stretched toward longer wavelengths. Over immense time, more galaxies disappear beyond the horizon, accessible to any one region. This process creates movement without a familiar traveler. The distance changes because the structure of space changes. Imagine a future so distant that the Milky Way and Andromeda have long since merged. The resulting galaxy has settled. The bright burst of star formation caused by the encounter has ended. Gas becomes less abundant. Many stars have exhausted their fuel. The sky contains fewer brilliant blue stars because massive stars live briefly and die quickly. Smaller red stars continue shining. They burn fuel slowly. Some may survive for trillions of years. Their light is faint, but their lives are extraordinarily long. Around them, planets may continue orbiting. Moons may circle planets. Asteroids may drift. The universe has grown darker, but motion remains. As stars age, gravitational encounters slowly rearrange galaxies. A star passing near another can exchange energy. One may be pushed into a wider orbit. Another may move inward. Across enormous spans of time, some stars can be thrown completely out of their galaxies. Others fall toward central black holes. A galaxy that appears stable over billions of years may slowly evaporate through countless weak interactions. Its members disperse one by one. The process is so slow that no human-scale comparison captures it properly. A star can complete immense numbers of galactic orbits before one encounter alters its path significantly. But given enough time, rare events become important. The future universe is shaped not only by common processes, but by events that require unimaginable patience. Planetary systems may also change. Stars passing at great distances can disturb comets. Planets exchange energy. Orbits become unstable. A planet may be ejected into interstellar darkness. Another may fall into its star. A moon may drift away. Tidal interactions slowly change rotations and orbital distances. The apparently permanent arrangement of a solar system is only one stage. Nothing guarantees that the same planets will remain together forever. Some worlds may become rogue planets, traveling through space without a star. They would carry no sunrise, no ordinary seasons, only internal heat, radioactive decay, or possible subsurface oceans beneath thick ice. These worlds would still move through the galaxy after their original systems vanished. The universe could contain vast populations of dark planets drifting between stellar remnants. Motion continues after light fades. White dwarfs would remain after many sun-like stars die. Neutron stars would persist after massive stellar explosions. Black holes would survive after some of the largest stars collapse and after dense objects merge. These remnants contain matter in extreme forms. They may no longer shine brightly, but they are not immediately inactive. White dwarfs slowly cool. Neutron stars lose rotational energy. Black holes interact gravitationally with surrounding objects. Pairs can orbit and merge. A dark universe is not automatically a motionless universe. It is simply a universe where movement becomes harder to see. Over periods vastly longer than the present age of the cosmos, even stellar remnants may change. Two white dwarfs might collide. A planet could strike a dead star. Black holes may capture wandering objects. Rare interactions can produce brief flashes in an otherwise dark future. An event occurring once in trillions upon trillions of years may become meaningful when almost unlimited time is available. The universe's final chapters, if time continues indefinitely, could be dominated by the improbable. Then there is the question of matter's stability. Protons appear extraordinarily stable. No confirmed proton decay has ever been observed, but some theories suggest they may decay over durations far beyond current experimental limits. If proton decay occurs, ordinary matter would not last forever. Planets, dead stars, rocks, and abandoned spacecraft would gradually lose their familiar structure. Atoms would disappear through rare particle processes. The universe would become increasingly dominated by lighter particles and radiation. If protons do not decay, matter may survive much longer. But even then, quantum effects and gravitational encounters could continue transforming objects. The exact far future depends on physics that remains uncertain. Current knowledge allows several possibilities, not one perfectly established script. Black holes may outlast almost everything else. A large black hole can survive for periods so enormous that ordinary numbers become nearly meaningless. Yet according to quantum theory applied to curved space-time, black holes are not perfectly eternal. They can emit extremely faint Hawking radiation. For a stellar or supermassive black hole, this process is unimaginably slow. The surrounding universe must become colder than the black hole before evaporation dominates clearly. Over a duration far exceeding the present age of the cosmos, the black hole loses mass. The smaller it becomes, the faster the process proceeds. Eventually, it may disappear in a final release of energy. If this picture is correct, even the darkest and most powerful objects have an ending. After the final black holes evaporate, the universe may contain mostly low-energy particles and radiation spread across enormous distances. The expansion of space continues separating regions. Photons stretch toward wavelengths larger than galaxies. Interactions become rare. Temperature differences decline. No concentrated fuel remains to power stars, life, or complex machines. This possible future is associated with heat death. The phrase sounds like destruction by fire. In reality, it describes the loss of useful energy differences. A machine performs work because energy flows from a concentrated or hotter state toward a more dispersed or colder one. A star shines because its internal conditions allow nuclear reactions and energy transport. Life depends on gradients, sunlight warmer than space, chemical differences, organized matter consuming free energy and releasing heat. When energy becomes distributed almost uniformly, fewer processes can produce meaningful change. The universe does not need to reach zero temperature. It approaches a condition where no large accessible difference remains to drive complex activity. Movement may still exist. Particles continue traveling. Radiation continues stretching. Quantum events may occur, but organized motion becomes rare. There are no bright stars, no warm planets, no large sources of concentrated energy. The universe is not absolutely still. It is close to equilibrium. This distinction is important. Heat death is not the moment when everything stops in a classical sense. It is the gradual disappearance of usable contrast. A photon may continue moving through space, but if it almost never encounters anything and carries almost no useful energy, its motion creates little structure. Particles may remain active quantum mechanically, yet no complex system can harness the activity. The cosmos could remain dynamic at the smallest level while appearing permanently silent at the largest. Whether true equilibrium can ever be reached is another difficult question. In an expanding universe, volume continues increasing. Radiation continues redshifting. Horizons limit which regions can interact. The final state may be approached without being completed. Much like absolute zero, there may always be some remaining process, however weak. Some particle traveling, some quantum fluctuation, some decay not yet completed, some region outside another region's horizon. The final stillness could remain infinitely far in the future. The universe would become quieter forever without ever reaching perfect silence. Other cosmic futures are possible if dark energy behaves differently from the simplest current model. If its influence grows stronger with time, expansion could eventually become powerful enough to overcome structures at smaller scales. Galaxy clusters would separate. Galaxies might be pulled apart. Stellar systems could be disrupted. In an extreme version, planets, molecules, and even atoms could be torn apart as the expansion rate increased without limit. This hypothetical ending is called the Big Rip. It would not produce stillness. It would produce increasing separation until ordinary structure could no longer exist. But this scenario requires a particular form of dark energy that has not been established. Another possibility is that the vacuum of space is not in its lowest possible energy state. The universe could occupy a long-lived but temporary condition. A transition to a lower energy vacuum might begin somewhere through a quantum event. A bubble of changed physics could spread outward close to the speed of light. Inside it, particle properties or fundamental forces might differ. No warning signal could arrive before the transition because nothing can outrun the expanding boundary. This idea is theoretical. There is no evidence that such a transition is approaching. It illustrates how incomplete our knowledge remains when predicting the ultimate fate of motion. The laws we observe may be stable forever, or they may describe one long phase in a deeper physical reality. The universe's final destination depends on the nature of dark energy, quantum fields, particle stability, and gravity. These are not small details. They determine whether expansion continues gently, accelerates catastrophically, reverses, or changes through processes not yet understood. Humanity has measured cosmic motion for only a brief moment. We are attempting to predict an almost unlimited future using observations collected during one tiny era. That does not make the predictions worthless. It makes uncertainty unavoidable. The same honesty applies when asking how fast we are moving today. We possess reliable measurements within defined reference frames. We know Earth rotates. We know it orbits the Sun. We know the Sun moves through the galaxy. We know the local group possesses a measurable velocity relative to ancient cosmic radiation. But physics does not provide an absolute universal speed belonging to us independently of all comparisons. The final lesson is not a single number. It is that movement is relational, layered, and woven into the structure of reality. Consider what your path looks like during the few minutes spent listening to this documentary. Relative to the room, you may barely move. Relative to Earth's center, your location follows a curved route created by rotation. Relative to the Sun, you travel along part of Earth's orbit. Relative to the Milky Way, the Sun carries that orbital path through a much larger arc. Relative to the local group, the galaxy adds another movement. Relative to the cosmic microwave background, the entire local environment has a measurable direction. The line traced by your body through space-time contains every one of these motions, yet no vibration announces them. There is no sensation of the galaxy passing around you, no wind produced by the cosmic background, no sound created by Earth's orbital speed. Uniform shared motion hides itself. What you feel instead are local forces. The chair supporting your weight, the floor preventing you from falling toward Earth's center. The atmosphere pressing around you. Small accelerations when you stand or turn. Human senses are designed for nearby changes. Cosmic motion must be discovered indirectly. We learned about Earth's rotation by watching the sky and measuring pendulums. We learned about orbit by following planets and understanding gravity. We measured stellar motion through tiny changes in position and wavelength. We mapped galactic rotation through the speeds of stars and gas. We found our movement relative to the early universe through a slight difference in microwave temperature across the sky. Every layer required greater patience and more sensitive instruments. Reality was moving long before we could detect it. Science did not create the motion. It removed the illusion of stillness, and the illusion remains useful. Daily life would become impossible if the mind constantly processed every cosmic velocity. To walk across a room, you do not need to calculate the Milky Way's path. To pour water, you do not need the expansion rate of the universe. Local frames allow us to live normally. The room can be treated as stationary because, for ordinary purposes, it is. The ground can be treated as fixed even though the planet rotates. A map can place north at the top even though space contains no universal upward direction. Simplification is not always deception. It becomes a problem only when we forget that a larger picture exists. The larger picture does not make Earth less real. It makes Earth more extraordinary. This planet remains stable enough for oceans to persist over immense spans of time while it moves through a changing galaxy. Life developed on a world that never occupied the same cosmic position twice. Organisms evolved while continents moved, the sun traveled, and the galaxy changed. Human history unfolded aboard a planet, racing through space without anyone feeling the speed. Ancient people looked at the stars and imagined fixed lights attached to a permanent sky. Today, we know those stars are suns following independent paths. Some approach, some recede, some have already died, though their old light still reaches us. The constellations are temporary alignments created by one viewpoint. The sky is not a ceiling. It is a moving three-dimensional history. Far in the future, the familiar night sky will vanish. Nearby stars will change position. Some will brighten as they approach. Others will fade into distance. New stars may become visible. Old constellations will become unrecognizable. Even if Earth could survive unchanged, its sky would not. Our visual sense of home is tied to one brief cosmic arrangement. The same applies to the Sun's place in the Milky Way. The solar system moves through regions containing different densities of gas, dust, stars, and radiation. Its exact path is shaped by the galaxy's changing mass. The Milky Way itself will lose its recognizable form during the encounter with Andromeda. Nothing in our cosmic address is permanent. Earth, solar system, Orion's spur, Milky Way. Local group. Each name describes a temporary arrangement of matter. The coordinates evolve, the structures merge, the labels eventually become historical. But change does not erase continuity. The material remains connected through cause and effect. Atoms created in ancient stars became Earth. Earth created the conditions in which life emerged. Life created observers. Observers built instruments. Those instruments detected motion across the universe. In this way, the cosmos developed a small region capable of measuring the journey from within. There is something remarkable about that. We are not outside the universe watching it move. We are matter inside it becoming aware of motion. The same physical laws guiding galaxies also guide blood through the body and signals through the brain. Gravity holds planets in orbit and keeps our feet on the ground. Electromagnetism shapes atoms and allows eyes to detect light. Quantum processes power stars and influence the chemistry of life. The universe is not a distant machine separate from us. We are one of its temporary arrangements. When we ask how fast we are moving, the universe is asking the question through us. Perhaps this is why the answer feels both scientific and personal. The numbers reveal speed, but the deeper meaning concerns position. We occupy no central point, no privileged platform, no region exempt from change. We live on one moving planet, around one moving star, inside one evolving galaxy. Our location is ordinary on the largest scales. Yet from this ordinary location, we have reconstructed extraordinary truths. We know the planet turns despite feeling stable. We know the galaxy moves despite appearing permanent. We know distant space expands despite seeming empty. We know that rest itself depends on comparison. Tonight, once the screen is dark and the room becomes silent, Earth will continue carrying you forward. During sleep, you will cross distances no human vehicle could travel within the atmosphere. The planet will move through its orbit. The solar system will advance through the galaxy. Ancient radiation will pass around you. Neutrinos will cross your body. Starlight that began traveling before recorded history will enter the atmosphere. Your personal journey continues without awareness or effort. By morning, the universe will not be arranged exactly as it was tonight. The difference may be too small to notice, but it is real. The stars have moved. Earth has moved. Light has arrived. Other light has left. Time has carried every system forward. So how fast are we really moving through space? Fast enough to cross enormous distances every second, slow enough that a single galactic journey outlasts entire species, moving at several different speeds depending on the object used for comparison, following paths nested inside paths, never occupying an absolute state of rest. And where are we going? Toward a new position in Earth's orbit, toward another region of the Milky Way, toward the future union of our galaxy and Andromeda, toward a more expanded and increasingly isolated cosmic age. But beyond every physical direction, we are moving toward the future. That is the only destination shared by everything. Planets, stars, galaxies, particles, observers, each follows a different path through space. All continue forward through time. Perhaps the universe will one day become almost completely dark. Perhaps motion will survive only as faint radiation and rare quantum events. Perhaps new physics will change the future in ways we cannot predict. But today, we live during an age of movement, light, structure, and discovery. Stars still shine. Galaxies remain visible. Planets orbit. Life looks outward. The journey is happening now, not beyond the window, not somewhere far from Earth, beneath your feet, inside every atom, across every level of the universe. You may feel completely still, but you have never been still. You were born aboard a moving world. You have traveled through the cosmos every day of your life. And long after tonight ends, Earth will continue carrying all of us silently into a region of space that no human being has ever visited before.